we're going to look at probability distributions for continuous random variable. Remember, a continuous variable is one that has an infinite number of possible outcomes. So far, we've represented the probability distribution of a random variable in a table, and we've even created histograms for the tables. Remember, the properties for these probability distributions are that they must sum to 1 and that all probabilities must be between 0 and 1. A better way to represent the probability distribution for a continuous variable is to fit a smooth curve over the histogram. We call this curve a density curve. Let's create a histogram for this data. I've done my best to fit the histogram in the space that I have to work with. Remember, you'd want to keep numbering 5, 6, and 7 out to the end. When we fit the density curve to it, it's going to run through the very middle of each of these points. The properties for this density curve match the properties for the probability distribution. The area underneath the curve must sum to 1. So if you shade under this curve from negative infinity all the way to positive infinity, that entire shaded area should add up to 1 or 100%. One difference, though, is that an individual outcome occurs with probability 0. The probability that x equals a particular value, let's say 1, would be 0 under the density curve, but if you look over here, it's 0.55 in the distribution table. Intervals of outcomes, however, do have a value. So if you're looking at a range of outcomes, let's say that you're looking for the probability of being between this value and this value, you will find that, and the probability of it will be equal to the area underneath the density curve. We're going to focus on the family of normal distributions. The notation for a normal distribution says that random variable x is normally distributed with a mean at mu and a standard deviation of sigma. For example, breeding season for the Florida white-tailed deer is from September to March. Gestation is 200 days when a litter of 1, 2, or 3 fawns is born. At 3 to 4 weeks, a doe brings them out of hiding. Fawns are weaned at about 3 months, but remain with the mother for 18 months. Average lifespan is 5 to 10 years. Natural predators include coyotes, bears, bobcats, alligators, and the Florida panther. The gestation period was recorded for n equals 10 deer. The mean gestation time was 200 days, so we know that x bar is 200, with a standard deviation of 10 days. So we know that S is 10. Assume that the data follow a bell-shaped symmetric distribution. We can create the density curve or probability distribution for this data. The center would be at the mean, 200. And the standard deviation can be used to gain 3 points to the left and 3 points to the right. The way you get the points to the left is to add the standard deviation, 10. 200 plus 10 is 210. 210 plus 10 is 220. And adding 10 a third time, you get 230. The way you get the points to the left is to subtract. 200 minus 10 is 190, minus 10, 180, and minus 10, 170. The empirical rule is this entire statement. For any bell-shaped symmetric distribution, 68% of the observations will lie within one standard deviation of the mean. When you read one standard deviation, I want you to think one tick mark. So if we label this on our diagram, between 190 and 210, that would be your one tick mark. We can put in the 68%. 95% of the observations lie within 2 standard deviations. Remember, you're thinking 2 tick marks of the mean. So from the mean, counting out 2 tick marks, that takes us to 180 and 220. 99.7% of the observations will lie within 3 standard deviations or 3 tick marks of the means. That takes us 170 to 230. You need to memorize this box. You need to memorize the percents and the number of tick marks that go with each percent. Let's look at an example. The first type of problem for empirical rule will give you a probability and ask for a value of the variable x. I've copied the picture to this slide. Between what two values will you find the central 68% of gestation time? We know that 68 lines up with one tick mark from the mean. So we should find these values between 190 and 210. That means 68% of deer will be pregnant between 190 and 210 days. 95% goes with two tick marks from the mean. So we know that 95% of deer will have a gestation period between 180 and 220 days. 99.7% of the deer will have a gestation time between 170, 3 standard deviations below, and 230, 3 standard deviations above the mean. What is the probability a mother takes more than 200 days to birth? In terms of notation, this is the probability that x is greater than 200. And this is the second type of problem. I'm going to give you a value of x, and you're going to give me back a percent. To do this, let's start by drawing a picture of what's going on. Here's 200. That was the mean on our diagram. And we want to know the probability of being 200 or greater. The mean breaks your data set in half. There will be exactly 50% above the mean, and there will be 50% below the mean. This is the property of symmetry. Your normal curve is symmetric about its mean. The upper half and lower half are mirror images. So just from observation, we can tell that this is 50%. What is the probability it takes a mother more than 210 days to birth? For these problems, you always want to start by labeling your mean. Then go and find all the numbers that go with 210. We know that 210 was one tick mark above the mean, and the number one tick mark below would be 200 minus 10, or 190. And from empirical rule, we know that if you're within one tick mark of the mean, 68% of your observations will lie within that interval. Now we're ready to shade the area. We want to know the probability it takes more than 210 days. That's 210 or more. That's the probability that x is greater than 210. Take the 100%, which would be the total area underneath the curve. So take your entire curve and subtract out the part you know about. You know about that central 68%. So what you have left over when you subtract it out is the lower half and the upper half. Now you know that this distribution is symmetric. So if you want only the upper half, divide by 2. Cut this number in half. That gets rid of the lower end and keeps the upper end, which is what you were looking for. What is the probability it takes a mother less than 170 days to birth? Always start by labeling your mean. Then go and grab all the numbers that go with 170. 170 was 3 tick marks below the mean. So 3 tick marks above the mean, we had 230. And from empirical rule, we know that within 3 tick marks of the mean, you will have 99.7% of your observations. We're now ready to shade the area of interest. We want to know the probability it takes less than 170 days. Shading this on the graph, that means we're looking for this value and below. Notationally, we're looking for the probability that x is less than 170. We know that the total area under the curve should be 100%, or 1. Out of this 100%, we know where 99.7% of it is. So let's subtract that out. When you subtract, that leaves over the lower tail and the upper tail. We're interested in only the lower tail, so let's divide by 2. That breaks off the upper half and leaves only the lower half, which is the portion that we were interested in. When you divide this out, the answer comes out to 0.15%. And just to avoid confusion later on, as a decimal, this would be 0.0015. This is a very small probability. This means values less than 170 could be considered very rare. Matter of fact, they could even be considered outliers. Same thing for values larger than 230. What is the probability it takes a mother between 180 and 200 days to birth? Always start by labeling your mean. Then grab other numbers of interest. Here, the only other number would be 180. And the values that go with 180 would be 220 and 95%. We're looking for the probability of being between 180 and 200. What we have is this section of the curve, which is 95%, and we broke this section in half. So what we're really looking for is the 95% divided by 2. This is 47.5%. This problem is special because the mean was one of the x values that we were bound between. What is the probability it takes a mother between 180 and 190 days to birth? We always want to start by drawing the mean and then drawing in values that go with the 180 and the 190. 190 is one tick mark below the mean, so we'll put in one tick mark above in the 68%. 180 is two tick marks below the mean, so we'll put in two tick marks above the mean in the 95%. We're interested in the probability of being between 180 and 190%. The way that we'll get this is to find the probability of being 190 and smaller and subtract off the probability of being 180 and smaller. This will leave over the portion that we're interested in. Maybe another way that would help you see it, if this is 190 and we find the probability of being less than this, and then subtract off the probability of being less than 180, that should leave over the probability of being between 180 and 190. Using notation, we could rewrite this as the probability that x is less than 190 minus the probability that x is less than 180. To get the probability of being less than 190, we'll use empirical rule. We know there's 95% of the data between 190 and 210. We know there's 68% of the data between 190 and 210. If we take 100 and subtract out this 68%, that leaves over the lower tail and the upper tail. If we divide this by 2, it eliminates the upper tail and lets us keep the lower tail. To find the probability of being less than 180, we'll use empirical rule. 180 is two tick marks below the mean, and so two tick marks above the mean would be 220, and by empirical rule, within two tick marks will be 95% of your observations. So if we take 100 and subtract out the central 95%, that leaves over the portion below and the portion above. To keep only the portion below, we'll divide by 2. That eliminates the upper half and lets us keep the lower half. This answer comes out to be 13.5%. What is the probability it takes a mother between 210 and 230 days to birth? Always start by labeling your mean. Then let's label the values that go with 210. That's one standard deviation above the mean, and we know 68% of our observations lie within that interval. 230 is 3 standard deviations above the mean. We know that 99.7% of our observations lie within this interval. We're interested in the shaded area between 210 and 230. To get this, we'll find the probability of being greater than 210 and subtract out the probability of being greater than 230. This should leave over the area that we're interested in. Another way to see this, if we find the probability of being 210 and greater, and then come in and subtract out the probability of being bigger than 230. That should leave over between 230 and 210 the area that we're interested in. Notationally, we'll write this as the probability that x is greater than 210 minus the probability that x is greater than 230. To get the probability of being bigger than 210, we'll take 100 and subtract out the central 68%. That leaves over the upper portion and the lower portion. If you divide by 2, you get to choose whether to keep the upper or the lower half. Here I'm going to choose to remove the lower half and keep the upper half. That division by 2 is breaking these two halves up so that you're keeping only one of them. To get the probability of being greater than 230, we'll use the property that the area under the curve is 100% and subtract out the central 99.7. That leaves over the area below and the area above. Since we only want the area above, we'll divide by 2. That lets us choose to get rid of the lower half and keep the upper half. This probability comes out to 15.85%. Here are the works cited used in this lecture.